We built the subscale reactor. Now we're talking about the calcium hydride storage system that we've worked on and we've got patents on. Several patents. This is a viable technology near term, and it's 20 times the storage density of the nitrate salts that you see that they're developing for very large scale solar. And basically what we're doing is we're taking sunlight. Now this is a reactor where we're electrically heating it. But what you do on a large scale system is you put sunlight through a quartz window. There's a quartz window on this. The sunlight would heat a chemical reactor on the inside, and that would, by controlling the pressure inside the chamber and the temperature, you can break apart the calcium hydride into calcium and hydrogen. What happens is the calcium rises and floats on the top of the calcium hydride until you completely filled the chamber on the inside with calcium metal. The hydrogen gets pulled off, we cool it down, we store it in hydride containers, which are just lower temperature metals that absorb hydrogen safely. And then at night, when the sun goes down, so we reintroduce the hydrogen, and what that does is it combines with the calcium, gives off a huge amount of heat, and then we take that heat and use it to run the Stirling engine.
So it's your battery.
It's a thermal-chemical battery, that's correct.
Right.
And for, to give you an idea, a 100 kilowatt system, which would, this tank is about 2 feet in diameter and 3 feet high. A 100 kilowatt system that would power 4-cylinder version of the engine for 24 hours a day, continuous, would be about 8 feet in diameter and 10 feet high. So this one's used to do our experiments to verify that the system's running, that we're able to get the power densities, the rates, and to really understand the physics of the calcium hydride reaction and all the metallurgy. Turns out we're using molybdenum on the inside of the reaction chamber to hold the liquid calcium at high temperatures. It's one of the few metals that works. So we're developing processes to make low-cost containers to hold the liquid calcium within this chamber. It's actually a triple wall chamber. There's an outer pressure chamber that's at room temperature. There's a middle chamber made of a stainless that holds the molybdenum chamber. So it's, safety is really an important thing. We're keeping that in mind so that if something was to spill, it would just stop inside the reactor and the reaction would stop. Also, calcium hydride degrades if it was to get released into the air into calcium carbonate, which is chalk. So very safe to the environment. We're not using any exotics or anything else that not only that you can't purchase, but that would be environmentally hazardous.
So this creates, okay, you've got a solar system on steroids then, basically.
That's right.
With a battery.
This is the battery, the chemical battery.
So you've got solar that while it's producing the solar, it's also producing the storage for the battery, right?
That's right.
And at night then it reverses and basically that storage moves back through. It's like a battery I've never heard of before.
It's a thermal battery.
Yeah. So, yeah. And it's obviously very efficient, huh?
95% for the 100 kilowatt, and for the 10 megawatt system it'll be 98%.
So then I think I heard that what, six hours of sunlight will possibly produce as much as 18 hours
of, right, so you can,
of storage of
that's right.
Wow. I mean, that's,
the reaction rates are very high. Actually, we're looking at applications where you can take all the power out in 1 hour instead of 18 hours if you wanted to, in order to follow, let's say at night when everybody needed power for cooking or something, you need extra electricity, you could use this to tailor your load. There's groups looking at that because if you can sell electricity during the prime time, you could sell it for a lot more money versus at night where it's lower cost. So there's different markets you're going into with this. It's very versatile and it's very economical. To give you an idea, we can build these and get them into production for the same cost as pumped hydro, which is really the only economically viable storage system that people are using in the United States. So it's really a breakthrough in power storage.
Wow. Now, to try to explain, you've got the solar collectors, your big old plates, as you see. What do you call those?
The dishes. I have a model over here.
Okay. And then you've got that, and what you do is you send that heat through these. They look like satellite dishes, isn't that?
Well, I'll show you.
Okay, you'll show me. Okay, good. So anyway, what this is though is this where you collect the intensity, right?
Right.
Down this.
The window.
It's zeroed down through here, the intensity of the heat. And what did I see? It was something like 7,200 suns.
Yeah, 7,200 suns. These quartz windows will take 10,000 suns. You can pass that much heat, that much sunlight through that quartz.
Yikes!
And which is really a lot of energy.
Holy cow!
This is just half-inch stainless.
That's pretty massive. Okay, cool.
This is a model of our dish. So we built this for wind tunnel testing to check out the loads when it's.
I'm just going to walk around
yeah,
it.
That's fine. The way it works, and there's wires that are going to be hooked so that this can be assembled rapidly in the field. Again, we're looking at the whole thing about maintenance, assembly, low cost, very high reliability. It all fits into this. And we also rolled in some advanced optic systems. So what we have is a parabolic dish. So this thing tracks the sun, and the sunlight comes in and takes this. This would be 43 feet in diameter for our dish.
Wait, it hits this before it hits the other plates?
Yeah. So it hits here
first. Oh, really?
This is our first mirror. Okay.
Oh, wow.
It focuses it into a cone that hits this hyperbolic mirror. Okay. So what that does, the hyperbolic mirror takes this sunlight that's concentrating. So we do half the focusing here, right at the dish. We focus it down to about a 6-foot diameter beam. If this was 43 feet, this would be about 6. We're taking that and then we're bouncing it off of a tilt mirror. So this is a computer-controlled tilt mirror where you can actually aim the sunlight in any direction you want. So this thing would always track the sun, and then you can aim the beam. The reason that
now this is just a mock-up. This is
a wind tunnel model, actually.
Okay, so it's not the actual thing because
it's a 2-foot version.
It's much more crude than it would be in the application. I didn't want.
Right. So again, the version that we'd be building is 43 feet in diameter with these pie-shaped mirrors, and they're all cast. We're using this is another example of keeping the cost down. We're tying in with Janicki Industries up in Sedro-Woolley.
Oh, that's where I live, up in that area.
Yeah. We've talked with Janicki for years now on this. They're going to fabricate our dishes for us.
They're amazing.
They're amazing. They're doing fuselages for Boeing. They're doing the windmills that you see all in the deserts.
Oh, is that right?
Oh, yeah. So they're very low-cost manufacturing. The man's brilliant. And we're applying that same mold construction technology to our mirror surfaces so that he can make very precise molds. We can get low-cost dishes. So it's all part of integrating into making it real. It's not magic.
Their reputation is
unbelievable. Their reputation is incredible. So we're teaming with groups like that. For our tanks, we're teaming with Alaskan Copper Works, who do the nuclear plant tanks, and they're also pressure vessel rated. So we're using 3 large companies that can allow us to grow very rapidly to create the viable growth and basically the learning curve, push the price down as quickly as we can to get the biggest value to the customer.
It's awesome.
Think of it as next generation solar. What we're creating is we're taking as much sun as we can, and we're getting 36% of that back as electricity.
So what you're saying is you don't need a half acre of field or necessarily to do what the other plates, plus you have to wipe them off all the time and this and that and the other thing. This would be much simpler. So what you're doing is again putting the solar collection on steroids again with this little, just like the little dishes for DirecTV, for instance.
That's right. That's right.
Okay.
We're doing things like self-cleaning surfaces. They've done things like they've got special coatings you can put on so water cleans the dust off. So things like that go into the low maintenance that give you a product that can sit and last for years. So we're definitely looking at going into the market with some quality equipment.
Wow.
So we've done work to develop molybdenum tanks. This is an example of some of the process we've been developing. This is actually, there's a 1/4-inch molybdenum shell within a stainless shell. So what we did is we started with a flat plate, and we went to a company back in Texas called Trinity that commercially makes these domes. Except they typically make stainless domes, right? But we needed to make a molybdenum one. Well, molybdenum, you can't heat it up in air. It has to be in a vacuum or in inert atmosphere. So what we did is we wrapped a stainless shell around it, and then they bent it, and see, it's in there. So we take the shell off, and we got our part. Low cost approach.
And I don't know what molybdenum is
I'll show you
used for. So
well, it's a high temperature metal that. Well, this is an example of molybdenum. In our heat pipe for the system, this is molybdenum with lanthanum oxide in it.
wow.
We just got, this is molybdenum wire, 2/1000 of an inch. We're going to make a mesh like a Brillo pad that's used to wick lithium metal. This is part of the heat pipe. So we've got a group that'll weave this into imagine a cylinder that's a 1/4 inch thick that fits inside the pipes we're going to make. What happens is the liquid metal wicks onto these surfaces and fills the tube. So it's just part of the process. We had a group in India do this for us. Nice, huh?